Thank you. Welcome, everyone. Good morning and good evening to all of you around the world. So welcome to the Diamond event. In the keynote, Partha asked who is new and for whom is ITC the first event, the first ITC, and my hand went up. So I am new to this community. It's a privilege to be here, my first ITC. And today we are here to talk you through some solutions to the sort of challenges that Partha was talking about. My talk is titled DFT to In-Life Monitoring for Dependable Electronic Systems. And Partha talked about trust in the hardware that we build as a community. So that's where the dependability links in. If you look back a few years, about 11 years ago, Mark Andreessen wrote a column in the Wall Street Journal saying why software is going to eat the world. And it has come true. In the last decade, we've seen that software has pervaded every aspect of our life. Now, this software, the progress that we have seen, is based on ever-changing and ever-advancing hardware, which is the industry that we are in and which is where we come in. That hardware goes all the way from sensors to really fast communications and into the cloud, the data center, the wafer scale computing that the keynote speaker Partha was talking about. Now, underlying all of this hardware is data. That's the lifeblood of this very rapid digitalization that's going on all around us. How do you generate this data? How do you transfer this data? How do you store this data? How do you make sense of this data? This is what we see all around us. And that's where the ever-changing, ever-advancing hardware comes into the picture. So the hardware needs to be high-performing, it needs to be dependable, it needs to be secure. And what's driving all of this is at Tessent in Siemens, we think of it in terms of three fundamental pillars: transistor scaling, design scaling, and system scaling. I'll walk you through an example of each one of these items and also introduce speakers for the rest of this event. So let's look at technology scaling. We know that Moore's law has been slowing, but that then led to multi-core SoCs so that you could just get a lot of job throughput done over multiple cores. The question to this community is, can we test multi-core SoCs reliably? What are multi-core SoCs? You think about an AI application for inferencing, for learning. These are thousands of cores that go into a single SoC, like the graph core and the Bitmain example shown over here. These cores, even before you get to these multi-core SoCs, the cost of test is typically about 5 to 15% of the overall development. Now, with these multi-core SoCs, if we were to do nothing, if there were no advancements in DFT in our domain, then the tester reloads would further increase the test cost, challenging the power and access management during tests. So that's not acceptable. Why? Because our customers who are designing these multi-core SoCs, they need to manage the cost of test, and they need to ensure that these cores and these chips are highly energy efficient, even in data centers, not just mobile SoCs, but even the ones in the data centers need to be highly energy efficient. So with those goals in mind, as a community, our challenge is to control the cost of test for these large, complex, multi-core SoCs. So the graph over here shows that exponentially rising number of cores, but the cost of test is near constant. How do you do that? Listen to Dan Trock for Amazon AWS. He's the next speaker. He's going to talk to you about streaming scan network technology from Tessent and how it has helped his designs achieve this kind of cost efficiency. Next, think about design scaling. Beyond these monolithic reticle limit SoCs, you have to expand. And that expansion is happening from 2D to 2.5D and 3D, putting in more logic, but in chiplets for better reliability, yield, and so on and so forth. What you see over here is a 3D IC structure. It requires testing each die in the package, testing between dies, testing at the wafer level. The patterns must be applied at the wafer as well as the package level. So wafer sort, burn in, and then retest at the package level. Because it's not just about known good die from the wafer sort, you have to also make sure that the die, once packaged, is working correctly. So challenging from a test pattern delivery through the stack with efficiency and within power constraints. To achieve these aspects, we have introduced just yesterday a new product called Tesson Multi-Die. And one of the speakers following me, Vidya Neerkundar, is going to talk to you about that technology today. Finally, Martha spent quite a bit of time talking about system scaling, data centers, and so on. So these are a couple of pictures over here for things that we have discussed before. The one on the left-hand side shows the hardware, software interoperability leading to some issues like silent data corruption that Partha talked about. And essentially the point is that we've got to not just test at the time of manufacturing, but also keep monitoring these devices for in situ, what we call in system, but he called in situ testing and monitoring. Same thing applies for automotives with safety, security concerns that we need to address while these SoCs are in the systems at the edge or in a data center. So safety critical applications such as automotive, large data centers, they require periodic, high quality testing of ICs in system, as well as in-life monitoring and actionable analytics. So what do you do with this data? How do you make sense of this data? How do you act on it? These things are extremely important. So given all of these challenges from our perspective at Tessent, we are addressing these IC lifecycle challenges through our Silicon Lifecycle Solutions portfolio, through the lifecycle of the design through production, through in-life, with multiple capabilities, be it DFT, be it yield learning, be it system validation and debug, be it safety security systems or in-system test, as well as embedded analytics, where we have to offer an integrated development environment, IDE, for trace, debug, and so on and so forth. So welcome again to this Diamond session to ensure dependable electronic systems. Stay tuned and listen to the next speakers. Thank you.
Thanks, Ankur. At this time, I'd like to introduce our guest speaker, Dan Trock. Dan is a senior DFT manager and principal engineer at Amazon Web Services. Over the past 9 years at Amazon, he's been building state-of-the-art design solutions, DFT solutions. He's overseen DFT architecture, methodology, and design, and he's managed DFT teams and their execution for AWS custom silicon projects. Before that, he spent 10 years with Motorola and Freescale Semiconductor in design and DFT roles. Dan holds multiple patents in the area of DFT and has a number of publications in peer-reviewed journals. He's a summa cum laude graduate from the Physics and Electrical Engineering departments of Technion, Israel Institute of Technology. Welcome, Dan.
Thank you very much for the introduction. Good morning, everyone. So let me start by putting some context into why I'm here. People always ask me, people know the highly popular Amazon.com web application, and they always ask me what this has to do with silicon, DFT, and test. So at Amazon, we also have the AWS business, which is all about the cloud computing. And AWS is one of the largest cloud providers in the world. So we have lots of infrastructure, data centers, and hardware around the world, and we constantly designing, building, and shipping custom silicon units into those data centers. Yeah, so let me take you to a short journey of silicon innovation at AWS first. So we have 3 main product lines at AWS, and it all started with the AWS Nitro system, which is basically about a smart card that offloads the main server and runs various network-related and storage-related and security-related tasks to free up the server to run only the user's workloads. The other product that we have is the Graviton server. It's a homegrown AWS ARM-based Graviton server, which is very powerful and efficient, and it builds up an ecosystem very quickly. And the third product line we have is machine learning acceleration. So those who want to run cost-effective inference and training in the cloud can use those accelerators. So our typical chip would look like this. We have large chips with many cores and also many interfaces. You can see here DDR interfaces on the left and right sides. You can see PCI Express lanes at the top and the bottom. So we typically have lots of I/O, and this is great for testing. We use those I/O to drive massive amounts of scan data into and out of the chip. But this design is quite old. It's a couple generations back in time. A few years ago, we decided to go multi-die. And this is a hot topic. You know, just yesterday we had a great panel on this topic, and a lot has been said about it. I'm not going to get into the details of the motivation going right to that. I'm just saying for the fact that we're also doing that. But look what happened to our I/O that we so much enjoyed in the previous generation, that we have so many of them. Basically, all the DDR and the PCI I/O went away into the smaller dies, and in the center we are left with a large chip that has very few I/Os and has very low test bandwidth, but still it's quite large, and we need to drive a high volume of test data into it to test it. So at that point, we already knew about the SSN technology, and it was under development, and it was around the corner. So we thought it could really fit us, and this kind of design is good for this technology because first of all, we have many identical cores here, and we could take advantage of the Ocean Compare that SSN that comes with SSN. And the other thing is that we have very few I/O. So SSN can run over any number of I/Os, as few as you may have, and seamlessly. So you don't need to worry about anything, and no complications around that. So we decided to build the SSN design into this chip in parallel with the regular scan design. And this way we would have, first of all, we would have a good fallback plan in case something doesn't work out. And second, we would be able to do a fair comparison between what SSN design can do and regular scan design can do. And this is what I'd like to share with you today. So let's take a closer look on this chip. So we have more than 400 cores here. We were able to stick 150 GPI into it. It's not bad, but it's definitely not the 1,000+ I/O that we used to have in the previous generations of the design. So first thing we did, we increased the chain length from 300 to 1,500. And this is to reduce the amount of EDT channel inputs and outputs that we need to drive and observe in the chip, and try to manage it better with the few I/O that we have in this chip. Now, even after that, we would still have a large pin max, and we still have 23 different scan modes, or scan domains, test rounds, okay? So that would be 9 internal mode test rounds, and what's even worse, 14 external mode test rounds. So typically external mode is something that you do on top of everything, and it's just a small pattern set that you create in one round and apply it. But in this case, we have, because usually for external test, what you need is just to control the wrappers, right? You don't need to control all your scan design. But in this case, we have so many cores, we have so many wrappers that we need to control to test those interfaces between the cores. And we have very few pins, so we weren't able to control all the wrappers together, and we had to break this problem up into smaller pieces and test those interfaces in smaller steps until we cover everything. So this is a tricky moment here because it is, first of all, it's a lot of work. You need to understand your design very well. You need to know all the interfaces, not just the main ones that move the big data around, but also the small ones. Couple controls here and there that one core sends to another. You need to know all that. And of course, everything must be tested. So you need to make sure that every such small interface is covered and that you do control all the active wrappers on this interface together, and it's covered by one of your PinMux configurations. So this process is both time-consuming and also there is a risk here of missing out on something and eventually end up with coverage loss, okay? So by the way, this problem does not exist with SSN because with SSN, we always can control any number of cores, any number of wrappers with as few pins as you may have, and this problem just doesn't exist there. So another thing that we did, so 23 rounds of test is not great, and we tried to fight back on the test time by raising the scan shift frequency from 100 megahertz to 200 megahertz. So to do that, we installed a complex scheme of pipelines in the chip, and it's not just about intercepting those wires that travel long distances with registers. It's also about balancing all the pipelines to all the identical cores, because as you know, this is how pattern retargeting works. You need to have all your identical cores with the same number of pipeline stages to the I/O, and some cores are close to the I/O, while some others are far away, and you need to make all that balanced. And there's really a lot of work here, and I personally spent quite some time building all those pipelines and checking that everything works fine and reaching timing closure at 200 megahertz. And I would really not want to do this ever again unless I have to. But fortunately, with SSN, I don't have to do that anymore. So let's look at the SSN design in this chip. So here I show the data path, how it travels through this chip. So first of all, at the bottom part, we have the first ring of the SSN near the I/O. And from there, we have the branches. We can reach into those columns, one after the other, and this way cover everything. So what we have here, we have a single PinMux configuration. We don't need to play with those PinMuxes anymore. And we have natural pipelining. We don't need to worry about pipelines anymore and balancing because everything is pipelined. Every scan host is already a pipeline stage. So you just have this short hops from one host to another host. And sometimes if you want, you can also install a pipeline. It's all automatic and easy. And the clock speeds are much, much higher because of those short hops. So here, almost for free, we got to, we achieved almost 400 megahertz very easily. Whereas with the legacy scan design, we had to work hard only to reach 200 megahertz. Let's move on here. So the next thing I want to talk is the test power. And I want to start with a small example. This will be very useful for the next slides. So consider two cores, core A and core B. These are two identical cores. And assume that the SSN packet size is twice the bus width. So we need 2 bus clock cycles to load the full scan word in all the cores, and so that they could fire the shift strobe into the scan chains, right? So the shift is happening in every core just once in every 2 cycles in this mode. The internal clock is divided by 2 from the bus clock. Now, both cores are identical. They receive the identical packet. They do exactly the same job, but they do this at a different point in time, right? So how different? this depends on the delay of the packet, how soon the packet will get from one core to another. In this case, core B will receive the packet 3 cycles later after core A, okay? And we deliberately put that small pipeline in between these 2 cores, and I will explain why. So 3 cycles delay, when we work in divide by 2 mode, this means that in the steady state shift, both cores are strobing shift every other cycle, but because the delay between them is 3 cycles, they will be doing that at different phases in time. So we have 2 active phases of the bus clock, and the core A will fire shift at the first phase, and the core B will fire shift at the second phase. So they will never, their shift clocks will never be aligned. They will always be interleaved. And this is very good for power, okay? Because half of your design is doing shift, while other half is not doing, and the other way, instead of everything firing shift at once. Now let's see what happens in our chip. So here I will shortly explain the plot, but let's focus on the left side first. So we run a bus clock at 300 megahertz, and we run the shift clock at 150 megahertz, again, because the packet size is twice the bus width. And also here, we create this situation with 2 active phases of the bus clock. And we do it in such a way that every 2 adjacent rows in this grid will never be aligned on their shift clock, okay? So basically, in this plot, you can see the current profile over time. And current is equivalent to power, just multiplied by the supply voltage, and you will get the dynamic power that your vector is generating. So you see here 4 bus clock cycles, okay? And each pair of bus clock cycles is equivalent to 1 shift cycle of the complete design, right? We have 2 phases, 2 bus clock cycles, and half of the design is shifting in the first bus clock cycle, and another half in the second bus clock cycle. So you see 6 peaks of current here, and each peak is corresponding to a specific row in the design. Okay, so in the first bus clock cycles, we see 3 peaks that correspond to the even rows, 0, 2, and 4. And in the second bus clock cycle, we see the peaks that correspond to the odd rows, 1, 3, and 5. So the point here is that by playing with the pipeline stages on the data path, we are able to spread out the edges of the shift clocks and make a smoother power profile generated by our vector. And this gives better power margins when we apply this test vector. Something else to note here is that, of course, when we look at odd cores or the even cores, and they all shift in the same bus clock cycle, but you still see a slight difference in time between those 3 rows. And this is because the clock also has propagation delay, right? So this also helps. But it's not something unique to SSN. It's always the case. So, but both of these 2 factors, the clock propagation delay and the phase we deliberately create between portions in the design help us create a smooth power profile and have better margins in power. So let's see how it looks in silicon. So here we compare, you see 2 Shmoo plots. So on the x-axis, you see the frequency of the reference clock. These are at-speed test vectors that we apply. And on the y-axis, you see the minimum voltage required for the test vector to work properly. So you can see that at the same frequency, the vector of legacy scan with aligned shift and capture is actually requiring a higher voltage to work properly than the vector with the staggered capture in SSN. And this, despite the fact that the SSN will test the complete design, all the chip at once, 35 tiles plus more cores around them, while with the legacy scan design, we are testing here just one domain, the column that is enclosed with this white box that you're seeing there, just 7 tiles. This is all we test. And the minimum voltage required to apply that vector is even higher than what SSN requires for the complete chip. Okay, so this is a little bit counterintuitive because you kind of test more with less, but I hope you now understand why and how it happens. So let's talk a little bit about optimizations in the packet that help reduce test time. So here, so we have two things here. One is on-chip compare, and the other is throttling of the packet. So I show here first the full chip packet size before they enable the on-chip compare. So it is more than 2,000 bits. This is about all of the EDT channels that we need to drive and absorb in the chip. That's what this number stands for. So once we enable on-chip compare, and since we have many identical cores, that packet size shrinks dramatically to 355 bits because all those identical cores are sharing the same slots in the packet, both on the input side and the output side. So this is a great reduction of test volume. Next is the throttling optimization. So throttling optimization is about managing the bandwidth of each and every core in such a way that cores that have lots of test data, they will receive many slots in the packet, whereas cores with less test data will receive fewer slots in the packet because they have less work to do, so we can slow them down and make them work slowly. In the end, they will finish more or less about the same time when the big cores will finish with lots of work. So everything will finish more or less aligned, but our packet will become shorter, and we will send the same amount of packets, but the packet will become shorter, and eventually the test time will go down. So throttling optimization here reduces the packet further by 1.7x down to 204 bits. Let's talk a little bit about test time. So for reasons of confidentiality, of course, I cannot show you the actual test time of these parts, but I can show you the reductions that are resulting from moving from the legacy to SSN. So in terms of test cycles, we have reduction of 2.3x, and this is a result of packet throttling and on-chip compare, as I explained earlier. For the clock frequency, we also run faster with SSN, so it's another reduction in test time by 2.4x. So that adds up in total test time reduction of 5.5x, which is very nice. Okay, and remember, we put some effort to speed up the shift frequency of the legacy scan design. And had we not done that, the speed up would be even greater. So the folks on the test floor are very happy about it, and of course we reduce the operation costs, and test time is money. You all know about that, and this is what we achieved. So I will conclude with what benefits we have gained from the switch to SSN. So on the design, from the design perspective, we need to do less planning upfront, and we just converge quicker to RTL freeze milestone. We have less risk of test coverage loss because even when we have few pins and many cores and large wrappers, we don't need to deal with breaking those up into smaller interfaces and manually building that big puzzle from small pieces. So with SSN, we test normally all the interfaces in one round. We have more robustness. Our top-level design is more robust because usually any change inside the core is encapsulated inside the core. So if logic changes there and you need to fix your compression, you need to add or remove some EDT channel, those things do not reflect to the top level, okay? So at the top level, you still have the standard SSN bus. This is the interface of your core, and nothing changes at the top level. So the top level is more stable and robust, and all changes are within the cores. That's another great advantage from the design perspective. From test time reduction perspective, as I showed you, we have 5x even more, and this is a result of higher clock speed and on-chip compare and packet throttling. And from the power perspective, we saw that staggered shift and capture clocks help make the power profile generated by our vector milder, smoother, and we have better margins, and we can test more with less, so the concurrency of tests improves. So that's pretty much all, and I will end this talk with a quote from our founder, Jeff Bezos, that every new thing creates 2 new questions and 2 new opportunities. So clearly SSN has cost. Okay, you will need to put some effort to make it work in your design. You will have some obstacles that you will need to overcome, but at the same time, there are obvious advantages here, as you have seen in my presentation. So I really encourage you to explore this technology further and see what you and your design can benefit from it. So that concludes my talk. Thank you very much.
Thank you, Dan. Our next presenter today is Vidya Nirkundar, Product Manager at Test and Silicon Lifecycle Solutions for Test Infrastructure in 3D. Welcome, Vidya.
Today, I'm going to be talking about advancements in DFT automation for 2.5D and 3D ICs. Before I do that, I want to start with an aerial view of a plot of land, and there's a house. So what happens if you need to expand the house? You have more requirements, you need to include more in the house. It's the obvious thing that we have done in the past, build a bigger house. And what if that's not enough, but that's not sufficient? You can't keep on building more, bigger houses. So what did we do? We created an extension. We created an extension in the house, and then we said, I'm going to connect the two together. It's in the same plot of land. And if that was not sufficient, we went vertical. We created another story to the house. And if that was not sufficient, we created another story. So in order to get access to these different levels, we had stairs. We just went using stairs from one level to another level. But what if the stairs was too slow? Then we had elevators. So, and what if you needed to have both the extension to the house as well as multi-story building, right? And that's exactly what's happening in our industry today. What we have in 2D is not sufficient. So we are expanding. And how are we expanding? We are expanding both in horizontal direction and extending to another device, another die, or we are also stacking up from one die on top of another, where the access mechanism happens only from the bottom die. And we are combining the two together, and we're calling that 5.5D according to 1838 IEEE standards. So we are not doing anything different than the plot of land where there was a house. We are just exactly following that. We're just doing 2.5D, 3D, and 5.5D. So what are the test challenges that we have? So the number one challenge for testing is what type of architecture, DFT architecture, are we planning to use for wafer sort versus the package? And what if these dies or chiplets, they come from different DFT architectures, right? You can get the die or a chip from supplier A versus a supplier B, and you don't know what the DFT is implemented in any of those dies or chiplets. And how do you retarget the pattern that you have obtained from each of these dies into the packet? And how do you schedule the test? So these are some of the challenges that we have in the test industry. Now, we introduced Tessent multi-die yesterday. We launched the product, and this is expanding the automation, what we know today in 2D, into 2.5D and 3D space. It extends the application of hierarchical DFT very nicely into 2.5D and 3D. And how it does that? By leveraging existing standards. We have IEEE 1149.1 for the tap access port, for the test access port or the tap. We have IEEE 1687 for IJTAG or internal instrumentation. And we have the new standard, which is 1838, which talks about test access for the three-dimensional integrated circuits. And that's what I have in the picture on the right bottom, which talks about primary tap and secondary tap is a mechanism that the 1838 says in order to access your stacked dice through a serial mechanism. The standard also describes a flexible parallel port, which you can go up and down the stack, but it's optional. But majority of the customers that we have talked to, they all want this optional flexible parallel port to be implemented because that gives them full flexibility. Now, going back to what test and multi-die does is if you have multiple dies in the package, like the picture on the top right, you have die 1, die 2, and die 3 next to each other. Each die can come with its own BSDL, which is boundary scan description language. But when you combine everything together into the 2.5D, you need one unified BSDL for the entire device. And that's what test and multi-die is going to do. It's going to extract from your individual BSDLs for each die and create one unified package level 1. And it's also going to create 1149.1 compliant patterns for the entire device. Now, you can also think about what about the interconnect between the dies? Yes, the test and multi-die can create boundary scan-based patterns for interconnect test as well. So those are some of the things that the test and multi-die can do, and it's launched yesterday. What else can it do? Well, it empowers access to each die. So when you think about you have a die, you can contact the die. Yes, you have wafer sorted it, so it's all good. You have a known good die. But once you put in a package, what happens to it? So the left column here talks about everything that can happen at the die level, which is the tan areas, right? If you look at the tan areas where you have the die by itself, yes, you can access the die, you can run any patterns on it, you can even use the test and streaming scan network, all the advantages that Dan talked about earlier, right? So all of that is good. But then when you stack them together, you need a mechanism to say, hey, I need to be able to access the middle die, some core in that, I need to schedule the patterns for it. And that's what test and multi-die empowers you to do. It allows test access to each die in the package and each core within the die, so that you can have access to all of the patterns that you have for each die at the package level. Now, the 1838 describes the flexible parallel port. And in the die level, yes, you can, the standard also talks about the serial access port, but what would you use as a flexible access port? We at Tessent have the streaming scan network, which Dan talked about why you should start exploring it if you haven't used it already. I'm going to be expanding that on how it can be used for 2.5D and 3D. So if you look at the advantages that it gives you for 2D, now you can extend it for 2.5D and 3D case because it decouples DFT for the core level and the chip level. Yes, you can extend that and say it's going to be decoupling my die level to the device level. And it's a huge benefit because it's independent shift and capture. Dan talked about he had so many cores, he had interleaving tests. That's naturally done with SSN. And it dramatically reduces your DFT planning. It has other advantages that goes with it. It eases timing closure, it's easier to route, 4x timing, test time reduction, volume reduction, as well as low pin count. You don't need to worry about accessing all of these dies from at the same time. You can access through the SSN bus. The bus is a symmetrical bus that goes up and down the stack. So all in all, what I'm saying is SSN is an ideal fit for your flexible parallel network or the flexible parallel port of the 1688 standard. The test and multi-die advances DFT automation for 2.5D and 3D. It is very effective and efficient in handling of multiple dies and chiplets, not only at the die level, but also at the device level. Suppose multiple standards, the very recent one being IEEE 1838, the 1687, and the 1149.1. It has complete access to each die, each code within the die, and all of the package, everything that you can access at the package level. It extends what you know best at hierarchical DFT in the 2D environment today into the 2.5D and 3D space. It utilizes the streaming scan network that's already out in silicon and proven, and is fully integrated with other Tessent products. You can have memories in the design that you need to be tested. Yes, it's fully integrated with the other products along with Tessent. And that's my last slide. Thank you.
Thank you, Vidya. Our final presenter today is Janusz Rajski. Janusz is the Vice President of Engineering of Tessent Silicon Lifecycle Solutions at Tessent Siemens. Welcome, Janusz.
Good morning, good afternoon, everybody. Since some people mentioned and even asked questions how many times and whether it's the first time you attend ITC, I'll have to make a statement. I've been attending ITC since 1984. So as they say, you know, I've been around. I met many of you at ITC. This is a phenomenal forum. And I learned listening to panels, discussions, papers, and on occasion, we presented some results of our own research. Every ITC, I remember there was something that I learned that was significant. But there's some ITCs that are special. Some of you may remember, and again, it's a quiz, you know, which ITC you attended. Some of you might remember fantastic keynote speech given by Pat Gelsinger, at that time, a CTO of Intel. Essentially, he said that the way cost of test is running out of control, at some point, it'll be as expensive to test a chip as it is to fabricate it. And that statement was consequential because it stimulated research. ATE companies, EDA companies, research community, everybody, you know, responded to this call. And as a result of it, we managed to develop technologies like test compression that significantly reduce cost of test and became fundamental repertoire tool, fundamental technology that we use today. And when I listen to some of the challenges, like the one summarized by Partha this morning during his keynote speech, I feel that this ITC is also special, okay? And in situations like this, you might also expect a statement from people who are developing tools like ourselves. What is our vision? How are we going to address those challenges? And this is what my talk will be about. So actually, the title reveals the topic that I'll be talking about: structural deterministic test in silicon lifecycle. So this is a talk about vision, if you like. A vision will not be worth much if it was just based on linear extrapolation of data practices that we've been doing in the past. A good vision should be long-term vision, should account for any discontinuities that we can think of, should also include innovation, because new solutions, they all require a lot of innovation. In our case, we also work with semiconductor companies to make sure that those solutions satisfy requirements and so on. And a vision based on those principles very often results, if you're lucky, results in solutions that have longevity. And that's what we like. When we propose something, we want this to be usable for many technology nodes. So what are the challenges, how we understand them? And I'm in a good position because some of those topics were already discussed in previous session and also in this session. So technology scaling presents a lot of challenges. The features are very fragile, you could say. There's a lot of new types of defects. Some of them are parametric at the border of process marginality. There are some technology-specific defects that the foundries know, and it's difficult to classify, but if you look at cells, you know that there are certain types of defects that are more common than others. There are reliability issues and aging issues, and those things need to be addressed. On design scaling, Dan gave excellent example of what DFT designers face when they work with state-of-the-art designs. They are very, very complex. And at the same time, we have to look at, when we generate patterns, we have to look at the level of transistors inside standard cells. So on one hand, the design is very complex, but on the other hand, in order to get quality, you have to get to the bottom of things. And since it is aging, it is a fact, well, we have to do something about it. So it shows again on this slide, architecting a solution, we have to look at aging, we have to look at reliability challenge, and we have to address those things. Functional safety, also another important aspect. So now DFT, we have to look at DFT throughout the whole life cycle, not only during design, during insertion, during manufacturing test, diagnosis, all of those things, but also during the life cycle of a product. I'll explain the other reasons for this, but we also have to make sure that DFT structures, which provide phenomenal controllability and observability, they are not a backdoor to security scan attacks. So Partha gave outstanding summary of some of the challenges. And we all heard about silent data corruption. And again, those statements made by by companies that operate very large data centers, they're consequential because pretty much I would assume that every CEO of semiconductor company knows about it and started a program to address those issues. So when I look at those statements, I gather it is a complex problem. So what do you do with a complex problem? Well, you divide it into smaller problems that you can handle. And hopefully you can come up with a platform that you could use across them, but you still have to look at them as distinct problems. So here are the 4 issues that we see. One of them is that cores fail at T0, which means that those are test escapes. So we have to improve the quality of manufacturing tests. The other issue is that we have early infant mortality. So what we need to do is we need to expose those defects and through stress test and make sure that we detect them during manufacturing, not when the chip is in the system. And finally, for random defects, we have to do periodic in-system high-quality tests. So how do you get high-quality tests? If you want to test every type of fault that is proven to be contributing to quality, you have to do it in deterministic manner. That's right. ATPG patterns. Patterns that ATPG generates, compression compresses, and then SSN packetizes them into packets. Those are the type of patterns that I'm talking about. And finally, we also have to monitor the aging process. So cellular test technology as many of you know, has been, in my opinion, the biggest contributor to the increase of quality of test in the last decades or so. It was a big change because until then, we worked at the gate level. It was a nice, convenient model, pretty abstract, but it was inadequate. So we started looking inside the cells. And that process requires, expensive characterization of libraries and so on, but it is a very good platform. And we see that this approach going forward by identifying new defect sites, by identifying what is the faulty behavior, and also optimizing patterns based on likelihood of those defects happen, that this will lead to further improvement in quality. Last year, there was a paper on multiple transition fault model. And again, that uses user-defined fault models. And we believe that there are still many improvements, significant improvements that can be made, especially in the time domain. As you know, in static timing and other areas, we're using single input switching. Multiple input switching is considered to be more complex, so therefore we do approximations and so on, but we believe that there is still a lot of room there for improvement. Now, the same level of thinking, looking inside the cells, gives us also great opportunity to provide tools for stress test. Burn-in test and stress test till now is again done at a higher level of abstraction, like toggling rate and things like those, but those are not adequate. Now, when we look inside the cells and we characterize them, and then we are able to simulate patterns and find out where the electrical field actually stresses, what features. Is it between a gate and source, gate and drain? So based on this type of analysis, we can develop like fault simulation tools. Once you have fault simulation, then the next step is how to generate those patterns so that we achieve high level of coverage, but with minimal number of patterns to minimize overstressing the design. For many years, the professional community recommended logic-based for in-system test. And I was actually one member of the community that was doing this, and for a good reason. And we still see a room for logic-based. However, if you look at the three most important criteria, evaluate logic-based, let's say, versus deterministic patterns, you see that in terms of quality, nothing can replace ATPG patterns where you have a defined fault model and you have automatic tool that can generate the highest quality coverage for that model or combination of models. Also, deterministic test that you store gives you ability to change it as you learn about defectivity profiles of a design that is in the system, or you may even have information about certain lots or certain period of time, certain processes have exposure to certain profiles. You can update those. Logic-based, on the other hand, shines in terms of volume of test data. There is very little that you have to store, but then is fixed. So we see room for both, but in order to address some of those problems like silent data corruption, we believe that deterministic tests will be required. So deterministic test will be very difficult to apply if we didn't have other technologies that we can base on, such as compression, orders of magnitude reduction in volume, such as SSN, and Dan talked about how much reduction we can get there, not only in volume and cycles, but also power, other things as well. So we envisage that for in-system deterministic test, we will be applying stimuli and getting responses, deterministic, using deterministic patterns to get desirable coverage. Now, SSN can also work in input streaming only mode with on-chip compare, and Dan talked about this in detail. So that will be further reduction, especially if you have identical cores, because it doesn't matter how many cores you have, the amount of data will be the same as for one core through just the virtue of the solution. SSN is really like SoC level structured DFT method. So you can see the building of scan, compression, and SSN. That's a nice hierarchy of technologies that we have at our disposal. And possibly we could also use a miser. We just have to make sure that we kill all the X's, but you know, that's a detail. And as Vidya explained, this actually, since SSN works very nicely with 3D, 2.5D designs, then using the same framework, we could use deterministic patterns as well. So now we're proposing that for a system, we have to do deterministic test in system and field, which means that we cannot burn our bridges. We cannot burn access to scan structure. It would not be advisable also to send stimuli and responses, because this would be, again, possibility for attacks, reverse engineering, and so on. So we need to protect those phenomenal DFT structures by providing root of trust. And again, we want to build this on existing technologies as much as possible. And in this particular case, we envisage that this will be built on top of SSN. So without it, we would store stimulant responses. Now, with root of trust, on the left-hand side, we'll store encrypted patterns, encrypted stimuli and responses. And the root of trust will have authentication protocol. And once it is successful, then the descrambler and scrambler will be programmed to deliver the original patterns as they were intended. But obviously, if the access is not granted, then there will be some random stuff applied for random configurations and things. So, in conclusion, as you know, every challenge creates an opportunity. And the same way as in the past, I think today the challenges will also create opportunities. Specifically, we see that one opportunity is to have DFT used throughout the whole life cycle of a product, from design, manufacturing, all the way in system test, in field test, including actually doing testing and diagnosis remotely. Because once you have something like this, and if you provide the infrastructure to communicate the responses back, then you could actually do remote diagnosis, and then you can learn, and so on. So, in addition, technology like this will stimulate other adjacent areas, such as hardware security, specifically for DFT. That, ladies and gentlemen, concludes my talk. There will be 2 technical presentations on hardware security that I'll give tomorrow, and another one on deterministic test on Thursday. And we will appreciate your feedback to the vision. So please don't hesitate to talk to my colleagues in the booth or wherever you can find them during coffee breaks, and give us your feedback. Thank you very much.
Thanks, Janusz. Thanks for joining Siemens and our special guest, Dan Trock, today. For additional information on the topics presented today, please stop by the booth. That's Siemens booth number 115. Talk to a Siemens representative. In our booth between sessions and during lunches, we'll have presentations on various topics presented by our technology partners, our customers, and Siemens representatives. Be sure to stop by and enter our daily drawing. Thank you, and enjoy the rest of the conference.